Okay, Bismillah ar-Rahman ar-Rahim, wassalatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. In the previous lectures, we have introduced regularization, which is a technique to reduce overfitting when you train a deep neural network. And the current practice is when we have a large neural network, in principle, it takes a lot of time in order to converge to a good solution. We cannot say optimal because we don't know what's the optimal, but let's say to a solution that would, okay, for us is satisfactory. And for this, there are several optimization algorithms that were proposed that will help you converge to the solution in a faster way. So in the previous lecture, we have introduced some techniques, like for example, the Xavi Initialization and also the normalization of the data, which are the techniques that we do in order to improve the conversions of the model. But there are also other algorithms that were proposed in the literature that can be integrated during the learning process that will allow you to converge much faster to the solution. Okay, let me first make a simple reminder of the previous lecture. In the previous lecture, we have started to talk about the optimization concepts in general, and can be summarized in the following. So first of all is the data normalization. Usually the data, it's multidimensional. So if we don't normalize this, may end up of having a computation problem during the learning process. So a good practice is always, before starting any training, we need to pre-process the data and make normalization. And there are different techniques of doing normalization. For example, here in this technique, we can divide by, subtract the mean and divide by the standard deviation. Some other technique, they may divide by the maximum value. For example, when we normalize an image, we know that the image pixels have values between 0 and 255. So we divide everything by 255, and this is going to give us values between 0 and 1 as a float number. And most of the techniques, they have the objective to put the data in the range between 0 or 1 or minus 1 and 1 within a bounded time, within a bounded range. And this will help the training algorithm to converge faster to the solution. And of course, this can be understood from the curve of the loss function or the cost function. Okay, when you do normalization, so the convergence will be much faster. You will have kind of circular shape rather than an elliptic shape like this, which make the convergence to the center here a bit more challenging. And another technique that we have introduced for the optimization is the Xavi Initialization. And in the assignment, you have observed that Xavi Initialization indeed leads to better training performance. Okay, and the idea here is to keep the variance of all the weights equal to 1 divided by n, and n is the number of nodes or units in every layer. And the way is that you can generate random values for the weight using the formula that will guarantee the following condition: the variance equal to 1 divided by n, and you have implemented this in the assignment. Okay, so you have observed that all these contributions from the scientific community in order to optimize the performance of deep neural network, because from computation perspective, there are a lot of challenges: the exploding gradient, the vanishing gradient, and the problem of convergence. It takes a long time for large data sets. So all these initiatives were actually tried to improve the training performance and the accuracy that will result from the model. So in today's lecture, we are going to learn a little bit more about the other optimization algorithms that are used in conjunction with the training process. And the learning outcomes are as follows. First, you will know the benefits of the learning rate decay and how to apply it to your optimization. You will remember the different optimization methods such as stochastic gradient descent, SGD, momentum, RMS prop, and Adam optimizers. So all of these are the name of what we call them optimizers. as I have shown to you now in the example of the CNN model. You also use a random mini batch to accelerate the convergence and to improve optimization. So first, let's get started with the mini batch gradient descent. Let's first consider that you have a very, very large data set. Let's say you have a data set of 5 million images. Okay, and let's say you would like to train all of them in one batch. So in this case, you will take these 5 million images into one batch and you will make a gradient descent. And when you finish the processing of all the images, you're going to make one, changing the gradient. You will calculate the gradient and make one pass of backward propagation. But the problem with this technique is not very practical when you have such amount of images, because it will be very slow. Okay, it will be very slow. You have to wait 5 million images into one pass in order to make one backward propagation. So the forward propagation will have to go through all the 5 million images, which is very, very large number. So instead of doing this, another technique, instead of processing them in one batch, we can divide the data set into several batches, or what we call mini batch. Okay, so let's say we can decompose these 5 million images into mini batches of 1,000 images. So the first 1,000 images, we can call them X1, and the second 1,000 images, we will call them X2, and here we put them between curly brackets. And at the end, the 5 million, if we divide by 1,000, we will find if we divide by 1,000, we will find that we will have 5,000 mini batches, and every mini batch will have 1,000 images. So in this case, what we will do, every pass or every epoch, we will have to calculate the forward propagation on just 1,000 images. Okay, so this will allow you to find the output Y1, and Y1 will correspond to the output of X1. Then you can go to the second mini batch, and this will allow you to find the output of Y2, and so on, until you go through all the 5,000 mini batches over here. And in every time when you find the output Y1, you will be able to calculate the loss for this mini batch. Okay, so for every mini batch XT and YT, you will be able to calculate the loss. Okay, and this will make at every epoch, so we can say that one epoch is when we process 1,000 images, okay, or one mini batch. At every epoch, you will be able to find the loss that corresponds to that mini batch. So in this case, how many gradient descent you will do in one when processing the 5 million images? How many backward propagation?
Depends on the number of batches.
Yeah, the number of batches is 5,000. So yes, you will do 5,000 backward propagation, and this will allow to make so you will have an update every 1,000 images instead of just waiting for the update after 5 million images. And of course, when we update, we're going to converge faster to the solution. Okay. Yes.
So that means after each batch you will evaluate?
Right. Yes. So if you remember when we did the classification project, for example, in the cut classifier or later, we can find the training accuracy, the training loss, the validation accuracy, and the validation loss at every epoch. So what is an epoch? Is the end of processing the mini batch. Okay. Now, for example, imagine that you have 200 images of cats. You can divide them into mini batches, for example, of 32 images. So after 32 images, you will have one output of the training accuracy, the training loss, the validation accuracy, and the validation loss. Yes, yes. One epoch, it means the complete processing of one mini batch. This is what we call epoch. Okay, so instead of waiting 5 million images to finish, to just make one pass of gradient descent, we're going to make a pass of gradient descent every 1000 images, which is much faster. Okay, so when you process the 5 million images, you have already done 5,000 gradient descent. So this means at every iteration you have converged toward the solution that you want. Yes, yes, yes. And here the input to the neural network will be nx 1000. Okay, because we have 1000 images and we have nx pixels per image. Okay, and this will make the total, the size of the total data set will be nxm, as we already seen in the previous lectures. And the output y is 1 because we have here a logistic regression in the case of logistic regression and through m training example. So this will be the output for multiple images here. Now this is the algorithm for mini batch gradient descent. Okay, so and when you have a large data set, mini batch gradient descent runs much faster than the batch gradient descent, as already explained. So it's basically the same forward propagation and backward propagation algorithm. The only thing is that here we're going to apply it on the batch, okay, XT. We will make the forward propagation on the batch XT. So instead here of having the whole batch, okay, or only one image, we will have just a mini batch. And for every mini batch, we're going to iterate over all mini batches. And in every mini batch, we are going to calculate the cost. And we can apply also regularization if we want. And finally, after finding the cost, we will calculate the derivatives. And we will make the update WL is equal to WL minus alpha dWL. And BL, the bias, is equal to BL minus alpha dBL. And of course, dW and dB are the gradients that were calculated in the epoch I. In every epoch, okay, in every epoch T, we will calculate a particular, the update, okay, the gradient with respect to GT. GT is the cost over here. Okay, and all of this, it represents one epoch of training. Okay, and one epoch is all of this, and this will be repeated 5,000 times. So to summarize, with batch gradient descent, a single pass through the training data set allows you to take only one gradient descent step, because you will have to wait the whole batch to be processed in order to calculate the gradient updates. In the mini batch gradient descent, a single pass through the training is just one epoch and allows you to take 5,000 gradient descent steps in the example that we have presented over here. Okay, so when you have a large training data set, the mini batch gradient descent runs much faster than the batch gradient descent on this large data set. But of course, yes. Epoch is when you process the 1000 images. This is what we call one epoch. Sorry. الباتش هو 5 مليون صورة. هذا نسميوها باتش. وال1000 صورة نسميوها ايبوك. اوكي، البروسيسنج بتاع ال1000 صورة. Yes, we have 5000 mini batches، لأنك 5 مليون على 1000 يساوي 5000. فهمت؟ هذا الإكس 1 هو ميني باتش رقم 1، الإكس 2 هو الميني باتش رقم 2، الإكس 5000 هو الميني باتش رقم 5000. من أين جاءت ال 5000 هذه؟ هي ال 5 مليون مقسومة على 1000. واضح؟ الإيبوك هو وقت اللي تتم معالجة 1000 صورة، سميه 1 إيبوك. هو على حسب، بعض الأحيان في بعض الأحيان يمكن يقصدوا الإيبوك لما تعالج كل 5 مليون صورة، يعني 5000 ميني باتش. أوكي، على حسب هل نعتبر الإيبوك هي الفول سكيل ولا السمول سكيل. فهمت؟ 1 إيبوك في السمول سكيل هي 1000 صورة، وإلا إذا كان ننظر على كل الصور هي الخمسة مليون صورة. نعم نعم، هو أصلا الإيبوك هي مقسومة، لو تشوفها تكون مقسومة هي أصلا على ستيبس، يمكن يسميوها ستيبس. نعم، 1 step. Yes, we can say this. Yes, now, following the TensorFlow, the epoch consists of multiple steps. Now we can say that the epoch may be all the 5000 mini batches, and 1 step is one executing 1 mini batch.
So when we say the complete processing of one batch, this is the definition of a step?
Yes. And here, yeah. I mean, okay, now you have to make لازم يكون عندك اصطلاح، لأنه بعض الأحيان الإيبوك أنا رأيت أن الإيبوك يقصد بها يا أما one pass على الميني باتش، and sometimes it's the whole batch gradient descent. Okay. لكن الآن احنا بالنسبة in this example we have to execute 1000 images. This is okay, we can call it الآن one step على حسب اللي موجود في TensorFlow, and 5000 this be one epoch. Okay, 1 epoch of training. هنا مثلا في الكورس اريا يعتبروا ال1 epoch it's mini batch gradient descent, only one mini batch. وفي الأخير مسميات. You can call it epoch, you can call it step. Okay, now if you want to consider here, like in this example, we can consider the step as processing 1000 images, and 1 epoch is the whole data set. Okay, yes, the entire loop. Okay, now what's the difference between the mini batch gradient descent and the batch gradient descent? Of course, for every technique it has its own its advantages and drawbacks. The good thing in the batch gradient descent is it is more consistent. I mean, the degradation of the cost as a function of the number of iteration is consistent. Okay, because at every step you are going to calculate the loss over the whole data set. Okay, so you're going to improve in every step, you're going to optimize with the whole data set. This is why here it's linear decreasing, okay, without any noise, because the optimization is made over the whole data set. Of course, considering here that we have a very large data set. In the case of mini batch gradient descent, it will also decrease, the cost will decrease as the number of iterations and also the number of mini batches. But the problem, it can be noisy, it can be fluctuating. Why? maybe you take the first mini batch and it will give you like a high cost. The second mini batch is a bit better, it gives you a lower cost. The third mini batch will give you a little bit higher cost, okay, because the optimization is made on different mini batches, okay, and it has to go through all the mini batches in order to make in order to decrease. However, here when you take the batch gradient descent, at every iteration it will take the whole data set, and this will make the optimization more consistent, because the optimization is made on the whole data at once, and here it's made on different data sets or different mini batches of the data set. Okay, this is why it could be a little bit noisy, but of course it will degrade. And the number of images in the mini batch is a hyperparameter. Okay, it's a hyperparameter, and you can choose it depending, so based on the observation that you have on the cost function over the iterations, you can either decide to increase or to decrease the mini batch size. Now,
So this will cause the training will take long time to make the cost look, make the cost less, because more time, right?
ما فهمتش السؤال متاعك. لونجر مش تقارن ايش مع ايش انت الان؟ No, بالعكس, the mini batch gradient descent, as I have already said before, it is faster. لا, it is noisy لكن it's faster. It's faster لأنه you make an update. You make an update every smaller number of images. Okay, so it will go faster, but of course it may fluctuate, because at every step, let's say at every step you are calculating a cost for a different data set. So it can be up and down, but this is in one epoch, but from one epoch to another it will decrease. Okay, but within the same epoch you can have some up and downs, because the cost is calculated on different images. You see what I mean? Yes. But the convergence of the mini batch gradient descent is faster, because at every step you are going to calculate a new gradient which allow you to move toward the solution. However, in the batch gradient descent, you have to wait until the whole images are processed to calculate one new gradient. Yes?
Doesn't it help that each time you calculate the factor of propagation, it will help the model to learn faster, a lot faster than the batch, because it will only do the factor of propagation only once.
With the batch gradient descent?
Yeah, after like finishing all the images.
Okay. Okay. What is faster? You calculate an update every 1,000 image, while you calculate one update every 5 million images.
No, doctor, I mean that when we have something to help us go the right direction, like in the mini batch, we're calculating after every mini batch. What I mean is, after we calculate the factor of propagation for the mini batch, will it help us convert faster for the next mini batch?
No, they are independent. I mean, every mini batch, it calculates its own cost, and then it will be averaged at the end. Okay, but every mini batch is like an independent data set. Okay, yes. This is, look, now you have 5,000 mini batches, and every mini batch is going to calculate its own cost and its own derivative. Okay, so W will be updated first from the first mini batch, and then will be updated by the second mini batch, and then will updated by the third mini batch until it is updated by the 5000 mini batch, and then it will be updated again by the first, and so on. It will loop. It will loop for several iterations. Okay, this is the algorithm here. For every mini batch, you will do the forward propagation on the mini batch, and everything else is the same. You got the point?
Yes.
Okay. And you do that for all the layers, Z1, A1, ZL, AL. And you calculate the update of the weight for every layer using the values of the gradient that you extract from the cost calculated with respect to this mini batch. Okay, this is why the mini batch gradient descent, it's a bit noisy, okay, because it will calculate a different cost on every mini batch. Now, how to choose the mini batch size? Okay, let's start with the extreme cases. Okay, the first extreme case is that the mini batch size is equal to m, the total number of images. And this is what we call the batch gradient descent. It means we are going to consider all images as one mini batch. And this is the same as the batch gradient descent. You will have as input the whole data set. Okay, this is the extreme case. The other extreme case is when your mini batch size is equal to 1, only one image. Okay, so you have 5 million images. You consider every mini batch as one image, so we will have 5 million mini batches. That's the other extreme case. And this is what we call the stochastic gradient descent. Okay, so the good thing in the batch gradient descent, it will have a consistent convergence. So it will go this step here and this step here, slowly, until it moves to the center. Okay, if we consider just here, just for illustration in two-dimensional space, but in general, the neural network is multidimensional. Now, if we consider the mini batch gradient descent, okay, so maybe for the first mini batch, it will converge, but the second mini batch, it will go a little bit far, then maybe the loss will be a little bit bigger and go then down. Okay, so it will go up and down the loss for every image. Every image is going to give you a particular loss value. Okay, this is why the convergence toward the point can make several zigzag here before coming to let's say not the optimal solution, but to the best solution that you want to achieve. Okay, this is the other extreme case. Yeah, just let me finish. I will open the room for the questions. And the balance that we can do is to take a mini batch size between 1 and m. Okay, so mini batch size now it becomes a hyperparameter that we have to set in order to have a compromise between the first extreme case, the mini batch equal to m, okay, which is slow, but it has less fluctuations, less noise, and the other extreme, which is 1, which is fast, okay, it has several iterations, but it has also some noise. So we want something in between. We can choose different values of mini batch size, for example, 16, 8, or 32, 128. So we can try different values. And this will provide a trade-off between the batch gradient descent and the stochastic gradient descent, which is summarized in this table. Okay, so for the batch gradient descent, it is too long per iteration, but it doesn't have any noise. For the stochastic gradient descent, it loses speed up of vectorization. So here there is also a problem in terms of speed, because we are going to process every image alone. And as you have already seen that in this case, we are not going to use the vectorized implementation. We are going to use a for loop. And this may also, from computation's perspective, it may be a little bit slower. But the mini batch gradient descent, it makes a good trade-off because it has a fastest learning, so it can learn fast. It has less noise also than the batch equal to 1. We can implement vectorization because we are going to process several images at once, and it will make progress without waiting for make progress without waiting while training set. This is the difference between the different techniques. Yes, if you have questions.
Sometimes stochastic gradient descent is used also available in library, I believe, in some projects.
Mm-hmm.
So is there a specific use case where stochastic gradient descent is best used?
Used in what?
In training.
Yeah, stochastic gradient descent that you have in training, it's the name of the optimizer. Okay, there is an optimizer that is called SGD.
Yeah, this is what I mean.
Yeah, but it's not the same here. Here it's for the mini batch size equal to 1. So we will talk about the optimizer later. I don't know whether they are using the same terminology for two different things, but the optimizer is something different. Yeah. Now here, the terminology here is batch gradient descent is for the mini batch equal to m, and the mini batch size, mini batch equal to 1 is the stochastic gradient descent. And the mini batch gradient descent, this is when you use a batch size between 1 and m. And when we have used SGD, if you remember, we have also used the batch size. صح ولا لا? Yes, yeah, so it's not the same as here. Any other question?
You make a batch size equal n. That means it's like one batch, right? All of them.
If you make the batch size equal to 1, you are processing the learning image by image. So you are not using vectorization. Okay. Yes.
The notebook we use mini batch, right?
We use a batch size, yes, greater than 1.
Yes, 64 or 32.
Mm-hmm.
This is mini batch size, right?
Yes. Other questions? Okay, so choosing the mini batch size, usually for small training data set, you can use the batch size, the whole batch size. I mean, you can use batch gradient descent. For large training data set, you can use a mini batch size gradient descent. Like you can subdivide it into, for example, 64, 128, 256, 512. But in any case, you have to make sure that your GPU is able to feed the whole batch size or the whole mini batch size. Okay, sometimes if you don't have sufficient memory in the GPUs, you cannot go to 64 or 128. Maybe your batch size will be just 8 or sometimes 16. Okay. In any case, the memory available in the GPU will be a constraint on the mini batch size that you can use for the training, because the whole mini batch size is going to be loaded in the memory.